Hello everyone and welcome to today's session. Let us shortly introduce ourselves. My name is Artur Jaworski and I am the Senior Software Engineer at CodiLime.
Hi, my name is Martin Parafiniuk and I'm a software engineer at CodiLime.
Today we are presenting the topic of generating packets with SmartNICs and P4. Before we get started, if you have any questions during the presentation, please type them into the chat on YouTube. We'll collect them up during the presentation and we will have time for questions at the end.
Of course, also a recorded version of this webinar will be available on our YouTube channel, so we invite you to take a look at that later. Let's begin.
Okay, so for today's webinar, we will be covering the topics about application for SmartNICs in networking data plane. Next, we'll present study case about our POC project, the packet generator. We'll be talking about the overall architecture of the solution, how we control the generator, how we generate the packets, and what is going on at the end of the pipeline. At the end, we'll draw some conclusion about our POC and the future of P4 itself. Okay, first let's talk about the application for SmartNIC. So one of the main applications of SmartNICs is in the networking area. Of course, SmartNIC with all the XPUs already exceed the networking use cases, but still SmartNIC holds its root in intelligent networking appliance. Creating SmartNIC application requires a platform that can handle both software and hardware development. And developers may want to create more complex application than just filtering, forwarding, or tunneling engines. One of the languages to handle those applications can be P4. But right now the P4 is mostly considered for the simple logic. But the data plane is a lot more than this. Developer may want to implement things like operation related to hashing, like recalculating or verifying the hash, operations which require stateful or the state, like in TCP session, the cryptography, or even non-event driven workload, like, for example, generating of the packets. But in those cases where advanced operations are required, P4 often is not the first choice language. We can ask a question, why? P4 provides basic functionalities expected to be in data plane description language, like table match action, archetype, header parsing and deparsing, or basic arithmetics for values. But currently the P4 is stateless by design. But with our POC, we tried to overcome, or you may say, suppress those limitations. And Martin, please continue.
Okay, so I'll talk about what specifically we did about generating the packets. So let's build a packet generator. So let's say we want to create an application that is going to create a stream of packets that is designed to stress test or feature test an infrastructure. If we would like to deploy this kind of application on a SmartNIC, we would probably have to target a specific SmartNIC, a specific vendor. SmartNICs are based on FPGAs or ASICs, so we would have to use specific features on that. If that feature is not available on an ASIC, it's either impossible to do it, or you have to write workarounds in C, which is rather cumbersome. If it's an FPGA, then you could possibly write it in VHDL or some kind of RTL, but these things are difficult, take time, and they're rather expensive. So, and also, whether you write for this or that, there is no portability between the two possibilities because these things don't correspond to each other anyhow. So we would have to if we would, for example, would like to deploy this application on multiple backends because we have multiple, types of SmartNICs in our server room, then we would have to basically write this application multiple times. So instead of writing this in a native technology, we would like to write the packet generator application in P4. So how would this look like? We have a host that runs a Rust application. We also, on this host, we have some hardware that supports P4, a SmartNIC that supports P4. And the communication between the Rust application and the hardware is realized by sending control packets from the app to P4. All of the heavy lifting is performed by the SmartNIC itself. There is no load on the host, so there is an, I would say, implicit performance gain. Even if the traffic itself is not faster than as it would be generated on the host, then the host resources are free to do anything else. So that's pretty nice. Also, if we would deploy this application on an XPU, everything would be contained within the hardware itself. So then you have a nice little box that you can just put into your host, and then it can be controlled in a very simple way, and then test your infrastructure by generating packets. What I would also like to stress here is that we are not, in fact, trying to build a traffic generator. Traffic generators are complex applications that have many features. They usually deal with streams where you can, for instance, have packets be modified somehow, or have them vary IP fields or whatever field you want. That is rather complicated. This was developed as a proof of concept, so we wanted to make it simpler, so we can only send traffic, receive traffic, and count the traffic, compare it to a given hash. The packets that come back from the tested infrastructure, we hash them and compare it to a given value. And we're not trying to call it a traffic generator. It's more like a packet generator, a simpler solution. Okay, so let's talk about specifics of that. We need some features to make this a reality. The most important set of features is recirculation and cloning. Because P4 is inherently an event-based system, an event-based architecture, there is no possibility of running a so-called while loop and just sending these packets in a continuous way. This is why we hack that somehow by using recirculation and cloning. We clone a packet and then recirculate it to the beginning of the pipeline, thus triggering the whole pipeline again, and creating this while loop by just circling this packet around. The other copy of the packet that was cloned is being directed to the tested architecture, and thus we create a stream of packets. Also, because P4 is an event-based architecture, the pipeline is cleared, is zeroed out every time that a new packet is handled. For that, there is a feature called registers, and registers are stateful, and that means that they can hold the value between different packets that are being handled. And we use registers to store the hash that we're comparing the traffic to, and some values like how many packets are left to send or whether we are generating the traffic or not. Additionally, we use counters and meters. This is actually rather simple. Counters are used to count how many packets we send, how many packets we receive, how many comply to the hash. And meters are a feature that this is something that lets you measure the speed of a traffic stream, basically the bandwidth, how many bytes per second are being sent, which in a traffic generator, a packet generator application is very useful. We would also like to offload hash calculation to the hardware. P4 can deal with all of the mathematic operations that you would possibly need, but we do not like to write this in P4 because first off, it would be probably faster if we did this in the hardware itself, and second off, counting hashes is difficult, and do not write your own crypto. Somebody already wrote it for you. It's probably better that way. So how do we control the generator? The REST application, as I have mentioned, sends control packets to the hardware. The control packets are basically like packets encapsulated in a UDP packet. So like at the beginning, you have the usual ETH, IP, UDP. And then our control header begins, and first it has a magic number. This is how the P4 knows that this is a packet that is directed to it, and not just a normal traffic packet that would be forwarded somehow else. And then we have values like whether we want to enable or disable the generator, what is the egress port that we want to send the traffic to, how many packets we want to send. This could also be set to infinity. And what is the hash that we expect on the other end of the pipeline? Yeah, that's it. This is the crucial piece of code that is responsible for like artificially creating this while loop that I've talked about earlier. If the conditions for generating traffic are met, which is that it's either we're set to infinity or there's like an amount of packets to send, we're cloning this packet and we're recirculating the clone packet to the beginning of the pipeline. What is not shown here in this code is that this packet that wasn't cloned, the one that we're currently handling, this is the one that is going to be sent to the architecture that we're currently testing. So one of the packets goes to the beginning of the pipeline, the other one is sent, and thus we're creating this while loop that P4 itself cannot currently manage. This is hashing of the incoming packets. This is actually rather simple. The stream of packets that is coming to the ingress or to our pipeline, we basically just invoke a hardware function to hash it, and then we read the register to retrieve the expected hash value, and then we compare the hashes. If the hashes are correct, then we increase the counter. Okay, so about the conclusions about P4 for SmartNICs. Okay, so we have a simple but not standard use for the P4 language. This is definitely a non-standard use case. Let me go back a few slides here to here, and like I'm just gonna quickly talk about like how these features were intended, because they were intended for like different reasons, and we kind of just like found them, and then like we came up with the idea to combine them in a new and unique way to create something new, right? So like recirculation was originally invented to decapsulate multiple layers of encapsulation protocols. So if, for instance, you have a packet that is like an MPLS inside a VXLAN, you can first parse and decapsulate the VXLAN, and then recirculate the packet to the beginning of the pipeline, parse it again, and then deal with MPLS. Cloning was, cloning is usually just called mirroring, and that's exactly what it was designed for. It's basically for mirroring a stream of packets to some other port in order to inspect it and see what's going on in there, right? So like these are things that like the P4 creators thought that they were doing it for it, but we used it in a new way. And like this is basically what we would like to talk about here. Let me just get back to the conclusion slide. If we had more features like this that would be available on the SmartNIC backends, it would be possible to create these like new applications of these features that maybe we don't even like think about yet. And this is why I think it would be important to add more features, to like standardize maybe more features or like generally support more of them, because P4 is a very cool and nice language. It's a very concise, very elegant language, I would say. And it would be nice if we could write more fun stuff in it. P4 is actually cool enough that people are using it for completely unrelated applications. For instance, physics photon simulations or neural networks. Like I've seen papers on it, which was really surprising to me because like this was designed to do networking. But P4 is very nice as a concept itself. So people are using it widely. Our POC was working only on the BMV2, which is a software implementation of the P4 pipelines of a P4 server. This is because, unfortunately, in our server room, there was no hardware that would be able to handle all of the features that we needed. And we did not want to develop new features as well. So we just ran it on the BMV2. It turns out that there are SmartNICs that would be able to run this, but we just were not aware of that at the time. So the existing, that's what it says, existing solutions lack features to run. That was done like half a year ago, and possibly new features were added to the SmartNICs that we had back then. I've also seen some new SmartNICs being developed within the last year. So like, we'll see, maybe something else is gonna happen. Something else is gonna appear on the market that is going to enable to run this on the hardware. Running this on the hardware would be also interesting because this would answer questions about performance. Our educated guess is that the hardware packet generation would be more or less the same or like a little faster than on the host. But we don't know that. We would like to see that in practice. Maybe it would turn out that the performance gain is significant, and this is why it's worth investing in that. All right.
Okay, I would also add the one thing, because we only considered the solution which has a public available documentation. Yeah?
Oh, yeah. Yeah. There's also like solutions that don't have public documentations. Like I'm not sure how much I can say here, so I'm not gonna say too much. But like there are SmartNICs that could run this. But yeah, this is all in the future. So I'm actually excited to see what's gonna happen.
Okay, so I will try to summarize this and put some light on the future about the P4. That we see that P4 for SmartNIC is currently is stagnant at the moment. And we saw that it is drifting more toward simple definition of the interfaces rather than data plane programming language. But we see that P4 is a good tool for what it was designed to do. And with the arrival of the whole new world of AI market, we expect that we will see a new feature for the P4 and for the SmartNICs, which of course can open the whole new world of use cases. We think that SmartNIC and P4 can be utilized to implement AI-oriented data centers, where quick and reliable connections between computes are crucial. Yeah, but this is topic for another webinar. Okay, now it's time for the Q&A. Do you have any questions?
Yeah, we invite you to ask us questions. There is a little bit of a delay between the stream and the audience, so like we expect to see the questions within about a minute. In the meantime, I also wanted to mention that it turns out that in today's times, when you have so-called AI factories, the data centers that are designed to use AI or generative AI, it's like even more challenging subject. the bottleneck is actually on the networking. So this is why the SmartNICs are very relevant, I think, because the GPUs are so fast that we're actually now blocked by the network. Okay, we have a question. You talked about the complex applications with P4 that require statefulness, but the P4 is by design stateless. Do you think P4 should become stateful? Okay, I'll take this one.
Okay.
Yes, P4 actually is not exactly like stateless by design, because in the 14 version, there were features that were not stateless. I'm talking specifically about registers. That was removed in the 16 version, and P4 pivoted from defining features to becoming a platform on which these features could appear. And this is, I think, what's actually the most powerful and interesting about this, that we could define a lot of new and interesting features that could include statefulness and all of the other things that we talked about, like cryptography and whatever, right? Okay, another question. Can you elaborate on how the hash is done? This is actually a very good question. That is the beauty of it, that we do not really know. We just offload that to the hardware. In the code that we wrote, we only call the hash function, and then something happens in the background. And this is it happens correctly, and it happens fast. So this is exactly what I would like to see in P4 in the future. That we could just.
Of course, we assume that.
No. It was fast. It was correctly. It was very fast. I definitely know that. Yeah, but that's what would be very cool about this. That if we could see like more features happening, that we could just like offload to the hardware and then like forget about it. That's definitely done well.
Yeah, I would say that because P4 is declarative language, you actually will just call what architecture is providing you. So, yeah.
Yeah. All right, we invite you to ask us questions. How do you know which functions are available in the hardware? Okay, so there are description files, right? For each architecture.
Actually, in P4, it's called the architecture. The P4 16 defines this. We have a portable NIC architecture and portable switch architecture. Those are the definition file which define the hardware capabilities.
Yeah. So
and all the manufacturers can freely extend those.
Yes, so like even though there are some standardized architectures that Artur has talked about, we could also extend that. So like the switch or the SmartNIC vendor actually provides us with the P4 file that describes the capabilities. Okay, let's move on. How fast are we talking about? How many packets can you generate per second? This is an amazing question that I would really like to know the answer to. Maybe we'll actually get back to this, because as I have talked about in the presentation, we were actually unable to run this on actual hardware because we did not have the hardware that would have the features, the capabilities, like recirculation that we would need to run this. So I think it's actually a good idea to get back to that and just kind of like deploy it on hardware and see what's going to happen.
Yeah, it would be really good idea. I would expect to actually go with the line speed. Yeah, I would expect this. For like when we have 100 gigabits per second SmartNIC to actually generate 100 gigabits.
Yeah.
Of traffic.
If that would be possible, this would be significantly better than software packet generators, which would give our solution a nice edge. Okay, another question. P4 as an additional level of abstraction can generate performance overhead. Don't you think that SmartNIC should be programmed as low as possible to get the best performance? Okay,
maybe I will take this. I think yes and no, because low-level programming gives the performance benefit, but has a few flaws. it is costly and it is not very portable. Yeah, P4 gives us portability in theory, of course.
Oh, yeah,
and and from the perspective of end user, of SmartNIC end user, who just want to smartify their data center, probably hiring a bunch of low-level programmers will be not worth it. Yeah, and also going with the low-level programming, you are locking on the single vendor, which can be problematic in the future. Yeah, and I think higher level languages can actually be faster because of common pattern optimization. As we can see with C and assembly, currently no one writes the performant part in assembler anymore, because with C and optimization of C language, we can get a much better result because of this.
Yeah. Let's move on to the other points. Performance must depend on the complexity of the P4 program. It is not per definition wire speed. So we need to understand the overhead that P4 introduces. Yeah, this is actually a very good point. This is something that Artur has just talked about. There obviously is some tool maturity that needs to happen and some optimizations that need to be introduced. Obviously, not every program is going to be wire speed because it depends on the program. That's what it's for. But hopefully, with having mature, reasonable compilers and competent P4 programmers, we could achieve wire speed, or almost wire speed, right?
Yeah.
Okay, we have to finish the session for today. Thanks a lot for coming, everyone, and listening to us. It was nice to talk to you, and have a good day.
Okay. For me, I have also a small announcement. After this webinar, you will get a very short survey about our impressions, about your impressions. Me and my team will be very grateful if you left us some feedback. Thanks to that, we can constantly improve our webinars, so thanks in advance.
Thanks again for joining us today, and we'll see you the next time around.
Thank you.